There is a rule in the ocean that nobody teaches in school. The deeper you go, the bigger everything gets. It is not an exaggeration. It is not a myth. It is a documented phenomenon that science calls abyssal gigantism, and it defies everything we think we know about survival. On the surface, an isopod fits on your fingernail. At 500 meters deep, it is the size of a football. On the surface, a squid fits on a plate. At 1,000 meters, it is longer than a school bus. Sea spiders the size of dinner plates. Tube worms 2 meters tall. Sponges the size of minivans. Everything grows. Everything inflates. Everything becomes a monstrous version of itself. And the most disturbing part is that science has theories, but no definitive answer. Something in the depths of the ocean makes animals grow to impossible sizes, and we still do not know exactly what it is. To understand this, you need to understand how the ocean is built. It is not one environment, it is 5 stacked on top of each other like floors in a building, each one darker, colder, more hostile, and more alien than the one above it. And at each level, the animals get bigger. The first layer is the sunlight zone, 0 to 200 meters. This is the ocean most people know. Warm water, sunlight, coral reefs, schools of fish, tuna, dolphins, sea turtles. Everything here is powered by the sun. Photosynthesis feeds the plankton. Plankton feeds the fish. Fish feed the predators. Life here makes sense. It follows the rules you learned in biology class. The animals are the sizes you expect them to be. Then the light disappears. The second layer is the twilight zone, 200 to 1,000 meters. Sunlight fades to almost nothing. The water temperature drops to between 5 and 10 degrees Celsius. The pressure increases to 100 atmospheres, and the animals begin to change. Jellyfish grow larger, squid grow longer. Shrimp that measured 5 centimeters on the surface now measure 15. The eyes of fish grow enormous to capture the last traces of light. Bioluminescence replaces sunlight. 90% of the creatures in this zone produce their own light. The ocean has become a living galaxy of floating blue and green sparks in a void of black. The rules of the surface are fading. Something else is taking over. The third layer is the midnight zone, 1,000 to 4,000 meters. No sunlight has ever reached this depth. The temperature hovers just above freezing. The pressure exceeds 400 atmospheres. And this is where gigantism begins to reveal itself in earnest. The giant squid lives here. Architeuthis ducks, up to 13 meters long, eyes the size of dinner plates, the largest eyes in the animal kingdom, evolved to detect the faintest bioluminescent flashes in total darkness. Its arms are lined with toothed suction cups that leave circular scars on the skin of sperm whales, the only predator brave enough to dive this deep to hunt it. For 2,000 years, sailors called it the Kraken. In 2004, scientists photographed it alive for the first time. In 2012, they filmed it. The monster was real, and it was bigger than the legends. But the giant squid is not alone. The midnight zone is where the rules of size break completely. Giant isopods crawl across the ocean floor at these depths. On the surface, their relatives are tiny crustaceans the size of a thumbnail, the pill bugs you find under rocks in your garden. Down here, they grow to 76 centimeters long and weigh nearly 2 kilograms, 2,000 times larger than their shallow water cousins. They look like armored aliens. They can survive up to 5 years without eating a single meal. When food falls from above, a dead whale, a rotting fish, they swarm it in the hundreds and consume it to the bone. The Japanese spider crab roams the same depths. Its leg span reaches 3.7 meters, nearly 4 meters from claw to claw. It is the largest arthropod on Earth, a creature that could stand over a human being with legs to spare. On the surface, its closest relative, the European spider crab, fits in a bucket. Down here, it is a walking nightmare with a body the size of a basketball and legs that stretch across a room. The fourth layer is the abyssal zone, 4,000 to 6,000 meters. The pressure here exceeds 600 atmospheres. The temperature is constant at 1 to 2 degrees Celsius. It is pitch black, and the animals do not stop growing. The giant grenadier fish cruises these depths, reaching over a meter in length, several times larger than its shallow water relatives. Sea spiders, pycnogonids, which on the surface measure a few millimeters, grow to 50 centimeters in leg span in the deep Antarctic waters. Dinner plate-sized arachnids walking slowly across the abyssal floor. Sponges at these depths have been measured at 2 meters in height and 3.5 meters in length, the size of a minivan. A sponge, an animal with no brain, no muscles, no organs, growing to the size of a vehicle. And then there is the final layer, the hadal zone, 6,000 to 11,000 meters, named after Hades, the Greek god of the underworld. The deepest trenches on Earth, the Mariana Trench, the Tonga Trench, the Kermadec Trench, pressures exceeding 1,100 atmospheres, temperatures near zero, absolute darkness. And somehow, impossibly, life is still here. Snailfish have been filmed at 8,000 meters. Amphipods, tiny shrimp-like creatures that measure 1 to 2 centimeters on the surface, grow to 34 centimeters in the hadal zone, 17 times their normal size. The deepest point on Earth still produces giants. So why does this happen? Why does the ocean make things bigger the deeper you go? Science has 4 main theories. None of them fully explains it. All of them probably contribute. The first theory is cold temperature. This is based on Bergmann's rule, which states that animals in colder environments tend to evolve larger bodies. The logic is thermal efficiency. A larger body has a lower surface area to volume ratio, which means it loses heat more slowly. In the freezing waters of the deep ocean, being bigger means staying warmer longer. Animals that retained more body heat survived and reproduced. Over millions of years, the cold selected for size. The bigger you were, the less energy you wasted on thermoregulation. The result was giants. The second theory is food scarcity. This sounds counterintuitive. If there is less food, animals should be smaller, not larger. But the deep ocean inverts this logic. Kleiber's law states that larger animals are metabolically more efficient. They burn less energy per unit of body mass than smaller animals. In an environment where food is scarce and unpredictable, where meals might be weeks or months apart, being larger means you can store more energy, last longer between meals, and cover greater distances in search of food. The giant isopod can survive 5 years without eating. A smaller isopod would starve in weeks. Size is not a luxury in the deep ocean. It is a survival requirement. The third theory is reduced predation. The deep ocean has far fewer predators than the surface. The crushing pressure, freezing cold, and total darkness create an environment where most predators cannot survive. Without the constant threat of being eaten, there is less evolutionary pressure to stay small and agile. Animals can afford to grow slowly over long lifespans, reaching sizes that would make them vulnerable on the surface, but are perfectly sustainable in the abyss. The deep ocean is a slow world. Things live longer, things grow bigger, things move less. Time works differently when nothing is chasing you. The fourth theory is dissolved oxygen. Deep ocean waters, particularly in polar regions, are rich in dissolved oxygen. Cold water holds more oxygen than warm water. More oxygen means cells can grow larger and organisms can sustain bigger bodies. This has been specifically linked to polar gigantism, where creatures in Antarctic waters consistently grow larger than their tropical relatives. The giant sea spiders of the Southern Ocean are a direct example. More oxygen in the water means larger cells, which means larger animals. But here's the truth. None of these theories alone explains abyssal gigantism. Cold temperature cannot explain why some deep-sea creatures in tropical trenches are also giants. Food scarcity does not explain why some well-fed shallow water species stay small. Reduced predation exists in many environments on land without producing giants. And dissolved oxygen levels vary across the deep ocean in ways that do not always correlate with size. The phenomenon is real. The pattern is undeniable. But the mechanism is incomplete. Something in the deep ocean, some combination of pressure, darkness, cold, time, and isolation, conspires to produce animals that are larger than they have any right to be. And after decades of research, science still cannot fully explain the equation. What we do know is this: the deep ocean is the largest habitat on Earth. It covers more area and more volume than every other ecosystem on the planet combined. And we have explored less than 5% of it. Every expedition to the deep brings back something that was not expected. Larger than expected, stranger than expected, more alive than expected. The ocean does not get emptier the deeper you go. It gets bigger, in every sense of the word. When Jacques Piccard and Navy Lieutenant Don Walsh descended to the bottom of the Mariana Trench in 1960 in the Trieste bathyscaphe, reaching 10,911 meters, the deepest point any human being had ever been, they expected nothing. They expected a barren wasteland of rock and sediment, crushed under 1,100 atmospheres of pressure, devoid of life. What they found instead was a flatfish calmly swimming across the bottom of the world. Life at the deepest, darkest, coldest, most pressurized point on the planet. Not just surviving, existing casually, as if 11,000 meters of ocean above its head was nothing. The deep ocean is not a dead zone. It is a factory. A factory that takes ordinary animals and, through mechanisms we do not fully understand, produces giants. Isopods the size of footballs, squid longer than buses, crabs that could straddle a car, sponges the size of trucks, worms taller than humans, spiders wider than dinner plates. Every level deeper produces something larger, something stranger, something that should not exist at that size, but does. And somewhere below the last point any human has ever reached, in trenches we have not yet explored, at pressures we have not yet tested, in darkness we have not yet pierced, something is growing. Something larger than anything we have found so far. The ocean has never disappointed in this regard. Every time we go deeper, the animals get bigger. There is no reason to believe that pattern has stopped. We just have not gone deep enough to find what is waiting.